Okay, so let's try to solve this problem number 62, unique paths or grid unique paths. So there is a robot on an m into n grid. The robot is initially located at the top left corner, grid 0 0. The robot tries to move to the bottom right corner, grid m minus 1 n minus 1. The robot can only move either down or right at any point in time. Okay, so either we can move right or we can move down. Given the two integers m and n, return the number of possible unique paths. Number of possible unique paths. So these keywords you need to note. And that the robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equal to 2 into 10 to the power 9. Okay. And the constant has been mentioned as m is greater than equal to 1, n is less than equal to 100. Okay. Now, what is the intuition behind this problem? The problem says the return the number of possible unique paths. Return the number of possible unique paths. And when we find this kind of keywords, which approach we can take? We can think of taking recursion. Okay, so I've already taken the grid over here. So here m is equal to 2, n is equal to 3. So how many ways we can move to the bottom right corner? So we have either we can go by right, down, right, or we can go by down, right, right, or we can go by right, right, down. So total 3 ways. Okay. Now the robot is located at the top left corner and it can either move down or right, right? So in that case, it can, to reach the cells on the first row, it can take one path, and similarly to reach the cells on the first column, it can take one path. Okay, so to reach the cells on the first row or column, it can take one path. Okay. Now suppose the robot wants to travel I comma j cell. Okay. Now to reach the I comma j cell, robot either needs to travel from I minus 1 comma I minus 1 comma j cell or I comma j minus 1th cell, right? From this cell or from top, from left or from top, right? So you can write to reach I comma j cell, the robot can take path either from I minus 1 comma j cell or I comma j minus 1 cell. Now let's discuss how can I approach to this problem. Okay, so we have written to reach the cells on the first row or column, it can take only one path. So we can have a function f I comma j, and we can simply write if I equal to 0 or j equal to 0, then return 1. Okay, so the first point is done then, and this is our base case. Okay, next point is to reach I comma j cell, the robot can take path either from I minus 1 comma j cell or I comma j minus 1th cell. So in that case we can say to reach I comma j cell, so we need to count the number of path to reach I minus 1 comma j cell. Plus we need to count the path to reach I comma j minus 1th cell. right? And if we call this function with f of m minus 1 comma n minus 1, then we'll get our answer. Now let's try to draw a recursion tree for this problem. Okay, so let's take if m is equal to 3, n is equal to 3, and we'll be moving from bottom. Okay, so either we can take left or we can take up. Okay, so let's take a function f of, so if we call f of m minus 1 3 minus 1 comma 3 minus 1, so if we will get f of 2 comma 2. Okay, so in that case we can take two positions, f of 1 comma 2 or f of 2 comma 1. Okay, then either we can take f of 0 comma 2 or f of 1 comma 1. Okay, similarly for this, either we can take f of 1 comma 1 or f of 2 comma 0. Then for this, either we can take f of 0 comma 1 or f of 1 comma 0. Okay, similarly for this, f of 0 comma 1 or f of 1 comma 0. Okay, now f of 0 comma 1, so this will return 1 as we have written over here, I equal to 0, j equal to 0. Okay, so this again f of 1 0 also return 1. Okay, so this will then f of 1 1 will return 2. Okay, f of 0 2 will return 1. Okay, f of 1 2 then will return 3. Okay, on the right we have this will return 1, this will return 1. Okay, and 1 plus 1, this will return 2, this will return 1. So 2 plus 1 will return 3. Okay, so total how many ways? 6 ways. Now what will be the time complexity for this solution? So time complexity would be 2 to the power m plus n, which is exponential, and then what will be the space complexity? So it will be m plus n minus 2, so which is the auxiliary stack space. Okay, which is the path length, we can say. So what is the path length over here? So we had m is equal to 3, n is equal to 3. So in that case 3 plus 3 minus 2, so 4. Okay, so we almost went for 4 levels, right, over here, 4 levels. Now as you can see in the recursion tree over here, right, so we are having overlapping subproblems. For example, f of 1 1 is matching with f of 1 1. And when we have overlapping subproblems, then we can think of optimizing with dynamic programming. Okay, so in dynamic programming we have two ways. One is memoization, another is tabulation. So we will first optimize with memoization and then we'll move to tabulation. Okay, now let's discuss about memoization or top-down dynamic programming. Top-down dynamic programming. Okay, so for this we will take memoization, means we already memorize the value, right? So we already pre-calculated or pre-computed the result into our memory, and then when we'll find the same problem again, we can use the memoized value, right? Memoized result, right? So for this we will take a 2D array of 2D DP array of size m into n and initialize with -1. Okay, we'll copy the same function over here. So f of I comma j comma, and we'll pass this dp array. over here. First, we'll copy the base case. If I equal to 0 or j equal to 0, return return 1. Okay. Now, if the result is already pre-computed, we already memorized the value, then we don't need to pre-compute. We don't need to compute again, right? So in that case, we can say if dp of ij not equal to -1, then we can simply return whatever the memoized value we have. Return dp of ij. Okay. Next, whenever returning, we need to store the result or we need to store the result into the dp array. Okay, so in that case, we can say return dp of ij is equal to f of I minus 1 comma j plus f of I comma j minus 1, right? So here we are using the memoized value. Here we are keeping the value into our memory. Okay, we are storing into a repeatable. Okay. Now, what will be the time complexity for this? So it will be m into n. So so this will be the time complexity. Okay. What will be the space complexity? So space complexity would be m into n. So we have taken a dp array of or 2D array of size m into n. And also we are still using the recursive or auxiliary stack space. So it will be n plus n minus 2. Okay. Now, how can I remove this extra auxiliary stack space? So which is m plus n minus 2. So in that case, we can think of taking tabulation, which is also called bottom up dynamic programming. Okay. So in case of tabulation, so we can think of taking a 2D DP table, so of size m into n. Okay. And this time we will initialize with 1. Okay. So let's take a DP table over here. So here m is equal to 2, n is equal to 3. Okay. Initialize with already initialized with 1. Okay. So initialize with 1. Okay. Now for this cell, so either we can move from left or we can move from top. So in that case, how many ways? So it will be 2 ways we can reach to this cell. Okay. Another case for this cell, right? So either we can move from top or we can move from left. So which will have 2 plus 1, which is 3. So you can simply write 3. So 3 is the answer. Okay. So if we return dp of m minus 1 n minus 1, we'll get the result. Okay. But you can see over here, so we took tabulation over here, so we are already storing the values in the table, and then when we are moving to the next step, we are taking the previous step value. So for example, when you are moving to this cell, so we have taken the value from the top cell and the left cell. Similar way for this cell also, we have taken from top cell and the left cell. Okay. So we are already pre-computing, we are already referring the values from the previous step. And again, when we are moving to the next step, we are reusing that value. Okay. So now we can write a for I is equal to 1 to m, for j is equal to 1 to n, right? dp of ij is equal to dp of I minus 1j plus dp of I j minus 1, right? And we can simply return dp of m minus 1 n minus 1. Okay. Now what will be the time complexity for this solution? So time complexity would be m into n, okay, and space complexity would be m into n, because we are still using the DP table of size m into n, okay. Now can we still improve the time complexity and space complexity? Let's check, okay. So we had taken m is equal to 2, n is equal to 3, and how many ways we can move? So we can either take right, down, okay, then we can take down, right, then we can take right, down, right. So 3 ways, right? And what is the path length over here? So it is m plus n minus 2, so it is 5 minus 2, which is 3, okay. And so in every step, like whenever in every way, so we are taking r 2 times or d 1 time, right? R 2 times, so R 2 times, D 1 time. So which is nothing but 3 minus 1 time we have taken R, and 2 minus 1 time we have taken D. So this is the maximum move we can take, okay. And this is out of this path length, which is 3. So either we can take 3C1 or we can take 3C2. So if we come out with this, then we'll be able to get our weights, like how many ways we can reach to the destination, okay. So which is nothing but m plus n minus 2 combination of m minus 1 or m plus n minus 2 c combination of n minus 1, okay. So now let's write the code. So f of m into n, okay, and here n is equal to m plus n minus 2, okay. R is equal to either m minus 1 or n minus 1, and we can take anything, okay. But in case R is bigger, right, it will take more time to calculate. So in that case we can check if R greater than n minus R. So in case over here here 2 is greater than n minus 2, so which is 2 greater than 1, so we can say R is equal to n minus R, okay. So which is we are basically swapping with 3C2 by 3C1, okay. Okay, so now we need to calculate the combination. So we can take, for that we can take a function I is equal to 0 to R. We can take a loop for I equal to 0 to R, and then we can have an answer variable as 1, okay, initialize 1, and then we can say like answer is equal to answer into n minus I, okay, and then we can say answer is equal to answer divided by I plus 1, okay, and then we can return the answer, okay. For this, so this is just to calculate the combination, or we can say NCR. I will create another video, another lecture for this, actually how to calculate combination, but just to save the time I'm just keeping as of now, okay. And what will be the time complexity for this? So time complexity would be minimum of m minus 1 or n minus 1, because you are swapping over here, right? So it will be minimum of m minus 1 or n minus 1, okay. And space complexity will having 1, so we are not using any extra space, so that's it, okay.